All right, let's get into it. Today, we're diving deep into a really critical document for anyone who builds anything, the Indian Standard 1892. This is the official playbook for investigating what's happening underground, and it's absolutely key to understanding the ground our entire world is built on. And when you see this mark from the Bureau of Indian Standards, you know we're talking serious business. This isn't just a set of friendly suggestions, it's the national standard. It's what ensures that the buildings, bridges, and homes we rely on are sitting on solid, well-understood ground.
Which really brings us to the biggest question of all, doesn't it? We can design these incredible structures above ground, but how in the world do we plan for the complex geology that's completely hidden from view? How can we build with any confidence on ground we literally cannot see?
Well, the simple truth is that every single thing we build, from a simple garden wall to a massive skyscraper, is totally at the mercy of this invisible world. Figuring out its complexities isn't just a good idea, it is absolutely essential for keeping things safe and stable.
And this is where geophysical investigation comes into play. You can think of it as giving engineers a kind of X-ray vision. Instead of just blindly starting to dig, they use these really clever, non-invasive tests to sketch out a first draft, a map of what's really going on down there.
And hey, don't just take my word for it. The code itself puts it perfectly, right here in section 5.1. These tests are the reconnaissance mission. They give you that preliminary information that helps engineers plan a smarter, much more targeted investigation. They don't replace drilling boreholes, they make it better.
So, what's actually in this high-tech toolkit? Let's take a look at the key geophysical methods that engineers use to unlock the secrets hiding just beneath our feet. Okay, so here's a quick look at the main tools in the arsenal. You'll notice each one measures something different about the ground. Some check electrical resistance, others measure something called primary wave velocity, which is basically just how fast a sound-like wave can zip through the material. You put all this different data together, and a surprisingly clear picture starts to form. All right, first up, let's talk about the Electrical Resistivity Test, or ERT. This is one of the most common methods you'll see out on a construction site.
Honestly, the best way to think about ERT is to imagine you're an electrician for the Earth. You pass a tiny electrical current through the ground and see what happens. Some materials, like wet clay, let the electricity flow easily, while others, like solid rock, resist it. It's this difference that lets you map out all the hidden layers.
Next in the toolkit is something called the Seismic Refraction Test, or SRT. And this one is all about sending vibrations, or waves, down into the ground.
This is so cool. You're basically creating a tiny, perfectly controlled earthquake. A source on the surface makes a little seismic wave, and then a line of sensors listens for it. Since those waves travel at different speeds through soft soil versus dense rock, you can figure out how deep and dense the different layers are. It's brilliant.
And the third major tool we're going to look at is ground-penetrating radar, which you probably know as GPR. You've probably seen this on TV shows when they're looking for buried treasure or something. And the analogy is perfect. It's pretty much an ultrasound for the Earth. It sends harmless radar pulses down into the ground, and when a pulse hits something different, like the edge of a buried pipe or where a layer of sand meets clay, it bounces back. This creates a live image of what's hiding right below the surface.
Now, it doesn't just stop with those three. The code also covers more advanced seismic methods. You can think of these as the specialized tools that engineers break out when they need even more detail, especially when the ground conditions are really complex.
Now, here's the really crucial bit about these advanced tests. They often measure something called shear waves, which are waves that move the ground side to side. This gives engineers a profile of the ground's dynamic properties, in other words, how it's going to behave when it's shaken. And you can probably guess why that is absolutely critical for designing buildings that can withstand an earthquake. Okay, so with all of this amazing technology, it's pretty easy to think, great, problem solved, but not so fast. As incredible as these tests are, they're not the whole story. They're a crucial first step, but they are definitely not the final word.
So, this brings up the obvious question. Are these tests enough by themselves? Can an engineer just run a few scans and then start designing a massive building? The answer to that is a very, very clear no.
You see, as the code makes really clear, these geophysical tests are reconnaissance tools. Their job is to give you that quick, big-picture overview of a site. They flag potential problem spots so you can plan a much smarter, more efficient drilling program. The data they give you is an amazing starting point, but it's an approximation that has to be confirmed by getting your hands on actual physical samples.
So let's bring this all home. Why does this whole systematic process matter so much? Well, because it's how we go from guessing to knowing. It's how we build on certainty, and that is the absolute bedrock of safe and cost-effective construction.
And this lays out the path perfectly. You start by mapping the unseen world with these geophysical tools. That map lets you target your drilling with surgical precision. Then you combine all that data to build a complete, reliable model of what's underground. And only then can you design a foundation that is perfectly suited to the ground it's going to call home.
Ultimately, that's the magic in all of this. We're taking these invisible forces, electrical currents, radar pulses, seismic waves, and using them to turn the complete uncertainty of a hidden world into the tangible safety of a solid foundation.
It really makes you wonder, right? Every single piece of land has this deep, complex story written in layers of soil and rock. So the next time you walk into a big building, just take a second and think, what hidden story is the ground beneath my feet telling?